1. Makes it so much simpler.
What is it?
I was just saying the denominator is just 1. It's so much simpler.
0.1.
Oh,
Negative 1.62.
Negative 100.
1.62.
Negative 1.62 units. Yes.
Newton meter.
Or Newton meters. The negative means something. It's not a directional thing.
this is called electrical potential.
Electric potential energy.
Electric
The electrical potential is something different because we've run out of words. What this is saying is that if I start with let's say I have a universe with a 3 microcoulomb charge in it. I have a negative 6 microcoulomb charge an infinite distance away. And I need to move that charge to that position right there. How much work will it take? Well, it's going to take negative 1.62 joules to move it here, in essence, at a constant velocity, or constant speed, I should say. No change in kinetic energy.
So, the negative 1.62, you could have a negative joule, or is that just indicating that it's losing energy?
It's indicating that there's an attractive force happening here. So that's why the work I would do is negative, because I need to slow it down. If I just let it go, it would get faster and faster.
Okay.
Now let's make it look more complicated.
Yes.
Yes.
Like, what are we measuring the energy of? Is it both the charges or just one of the charges?
Energy of the system.
Okay.
So it's the combination of the two. You don't really have potential energy of just a single object. There has to be something else involved. Because potential energy is related to conservative force. Forces require 2 objects. Let's do one other plug and chug, and then we will do a more complicated looking problem. I have a 3 no, I don't want that one. What the heck, let's start with it. A 3 microcoulomb charge here. And 0.4, that was 0.04 meters away, I have another 3 microcoulomb charge. Using the same convention of potential energy is 0 when r is an infinite distance. What is the potential energy of this 2-charge system?
It's obvious.
It is. And
It's 0.
not 0.
Darn.
There's 1. I'll reveal the units later.
You have to do the math, or is there?
Yeah, you have to do the math.
Okay.
Yeah, the simpler one's coming up. The one that looks more difficult.
Yeah.
2.025.
2.025. 2.025.
joules.
It is a repulsive force. In order for me to move that 3 microcoulomb charge from an infinite distance away, I have to do positive work.
Does it matter? I don't think it does, because we didn't do anything in the direction that it's up or down, or whatever way the line is.
Oh, yeah, we're dealing with scalars, it's simple plug and chug. Don't lose the minus signs. All right. Questions up to here before I make it look more complicated?
I'm still confused about what the negative means.
The negative,
point
all
on
right.
whether being positive or negative.
Let's go back to the work energy relationships. What are the 3 work energy relationships?
Work equals change in energy. Oh.
Which one equals change in energy?
Non-conservative.
There's one of them. Then we have work conservative and work total. The last one being the work energy theorem.
The work total is a change in kinetic energy. Then
Negative change in potential energy.
All right, those are the three work energy relationships, so let's concentrate on this one right here since we're dealing with potential energy. So if I have that, you were asking about the negative sign, right, Caroline? All right, so I've got my 3 microcoulomb charge here, and I've got my -6 microcoulomb charge here. That we'll consider an infinite distance away. When this charge moves from here to here, so when it's moving from there to there, the conservative work, the electric force is attractive, it's going to pull it straight towards it. So the conservative work done is equal to negative U final minus U initial, which is U initial minus U final, which is 0 minus negative 1.62, 1.62? Yeah. Which is 1.62 joules. The conservative work conservative work is positive, which means that it moved in the direction of the conservative force. All right, are you good with that?
Yes.
All right,
so when we're saying it's attractive, what is it being attracted to again?
the positive charge. It's a negative and a positive charge.
Oh.
Okay. So from that point of view, it's the negative of that. The negative of that is what the conservative work is. In this case right here, it's a repulsive force, but it's still moving from an infinite distance away to here. So the conservative work is negative because it's moving in the opposite direction of the force. So down here, my interpretation earlier, if the conservative work is positive 1.62 joules, and I want to, personally, I'm going to move it from there to here, where it doesn't change speed at all. So the change in kinetic energy is 0. Then the work that I have to do is negative 1.62 joules, because with no change in energy, no change in kinetic energy, the total work is 0. So the amount of work I would have to do to move it to here has to be whatever I add to this to get 0, which is negative 1.62 joules. There are other ways of looking at it. That's generally the way I do it. Okay. Okay, good, good. Other questions? Now, make it a little harder. I now have a 3-charge system. That's my universe right there. I have a 3 microcoulomb charge, 10.1 meters away. I have a negative 6 microcoulomb charge. And then another spot where it is 0.10 meters from the negative 6 microcoulomb charge and 0.04 meters from the 3 microcoulomb charge is another 3 microcoulomb charge. What is the potential energy of this system, assuming potential energy is 0 an infinite distance away? What is the potential energy of this, or how would you go about figuring it out?
Would you just add another number to that equation?
Oh, multiply Q1, Q2,
Just add a
Q3?
parentheses for the other one.
Sorry, I missed the last part.
Just add a parentheses for the other one? Or does that change because we have multiple distances? What I'm saying is just.
When you say added, all right, say it again.
So, just add another parentheses, like, so, for
Oh,
example.
okay, so tack on,
Yeah,
because units would change.
would you split it up into 3 parts?
Yes.
God.
You find the potential energy of this, potential energy of that, potential energy of that. And then what do you do?
Add 'em all up.
Yeah, add them all. So we've already done the hard part of this. I know the potential energy of this pair is negative 1.62 joules. Potential energy of this pair is negative 1.62 joules. Potential energy of this is 2.025 joules. And yeah, and you end up with negative 1.2 joules-ish.
No. Oh, it actually right
So you would just do what we did for each side.
Yeah, and just add. We don't have to worry about direction, which is nice.
Now, for like a quarter or something, could you do something more than 3 sides? Like, could you do 4 or 5?
Yeah, if I did 4, then I'm now adding. So I got those 3, then 1, 2, 3. So now I'm adding 6 of them together. 5. 9. It just, at some point, it just becomes a pain. Hey, all right.
Mike.
And here's an interrupt, any
Yes.
intellectual discussion we might have. There's our very own Mike Jones.
Yeah. Hi, everybody. I'm Mike. I'm a tutor with the Learning
Do
Center.
you want to be recorded?
Huh?
Do you mind if you're recorded?
I don't care.
Okay.
Do I get royalties?
Yes, I will give you half of whatever I get from this video.
Fantastic. Okay. So yeah, I'm a tutor with the Learning Center. Some of y'all know me. You've been in the STEM lab and everything. I just wanted to pop in for those who might be new between the sections, or maybe you just kind of forgot about the tutoring. And so I'm here as a reminder. We have, this is 152, right?
Yes.
Okay, I'm doing like 4 of these today, so I have to keep it on straight.
This is one of the important ones.
Right. So unfortunately for 152, I think it's basically just me right now. There's supposed to be a new STEM person, actually, like starting maybe this week, next week.
Okay.
That's nice. But so for right now, for physics, you have the STEM lab, which is over in Strickland on the 2nd floor in room 2343. Right now, the hours are 10 to 6, Monday through Thursday. And if you're coming in for physics, that's it for right now. I don't think we have any virtual one-on-one tutoring options either. But if you do have any classes like math, English, economics, business, whatever, we do have one-on-one tutoring, for that, both in person and virtual. So as far as, me, I had Dr. Fox, right, years ago now, for 251 and 252. So, and I've, been working with him for quite a while, helping out a bunch of y'all. I've done some of these labs 30 times at least with some students. And so I'm very, familiar with the material, I'm familiar with his kind of language and trying to interpret from what he is meaning in a problem to what y'all can maybe understand to help bridge that gap. Because sometimes when you have such a mighty and powerful brain, it is hard sometimes to come back down to the mortal realm with the rest of it.
Hey, I write assuming my audience is as awesome as any person is.
So that's basically it. Do y'all have any questions for me or about tutoring in general? Nope. Okay. I'm just gonna leave a few of these around.
Okay.
If anybody, this is stuff on how to make one-on-one appointments, and then just a little bit about the drop-in stuff. And I'll let you finish up. All right. See you, man.
See you later.
Our very own Mike Jones, or Michael, as I'm not sure what he goes by these days. He's constantly changing his name, staying one step ahead of the law. Questions?
Let's make it hard.
Was that?
Let's make it hard.
All right. And I know what you're thinking. And I'm going to express what you're thinking right now in a table. Who doesn't love a table? So far, we've talked about, I have two charges and we're talking about a vector quantity, we're talking about force. And so in the case of E, Q1, Q2 over R squared, R2. If we're dealing with just one charge, well, we're talking about electric field. And it is the electric field coming from two would be the force on one from two divided by the charge of one. And that's chapter 18. Chapter 19, we get to a scalar. If I have two charges, we're talking about potential energy, electric potential energy, and U sub E is KB Q1, Q2 over R. And you're thinking, wait, we've got a gap there. Suppose it's one charge and a scalar. What am I talking about? Well, you're in luck. There's an answer. When we went from force to electric field, we divided by what is known as the test charge. Well, we're going to do the same thing here. So KE Q over R generically. We have this quantity, KQ over R. Let's take a look at the units first. I know the units of force are newtons. The units of electric field are newtons per coulomb. The units of potential energy are joules. What will be the units of charge of this mysterious object?
Joules per coulomb.
But that, for some reason, is too much for physicists to write. Newtons per coulomb, they're fine with. Joules per coulomb, whoa, back up. A joule per coulomb is equal to a volt.
Another V.
Another V. Don't worry, there's another one coming up. This is not voltage. It's not voltage. Let me emphasize that, one of those words, not. This is electric potential. And this is why I distinguished earlier. There's a difference between potential energy and potential. So electric potential, or potential. If I need energy from now on, I need to use the word energy. If I say, what's the potential? I am now talking about this. I'm not talking about the potential energy.
What's the difference?
A Q and units. Now the symbol for electric potential is a capital V.
Physicists really.
Yeah, we ran out of letters.
Is there any way you can make that be special or just?
No.
No.
Well, yeah, there is a way I could make it special, but I'm going to quickly forget because I'm me. All right. So the following is a perfectly legitimate physics expression. The electric potential is equal to 3 volts. If you were presented this in math class, V would equal 0. In physics, that V and that V do not represent the same thing.
So the electric potential is 3 volts.
Yep, the electric potential equals 3 volts. It is unfortunate, but they did not consult me.
As they consulted you, would you change one?
I'd make one of them a fancy V or something, I don't know.
Headlines about the.
Generally, the way that you tell the difference between the two is that volts comes after a number, potential does not.
Okay.
All right, so, but we're talking about volts, and you presumably have heard voltage. I mean, if I have a 12-volt battery, is that the electric potential, or is that the voltage?
That's the voltage.
It is indeed. So what is the difference between electric potential and voltage? So if I have a particle here at some location where it is a 4 volts, and I have another location over here where the potential is 2 volts, and another location here where it's 0 volts. So it's just points in space with 3 different electric potentials. I take this and I move it to here. I don't care about the path I take. I just move it to there. What is the change in my electric potential? In other words, what is the electric potential difference?
-2.
That is voltage. The electric potential difference and voltage are the same thing.
So the change in electric potential is voltage.
Yes.
Which, does voltage, if you're like writing it down, like the voltage of this, is the letter for that also V?
Delta V. However, just to make it look more complicated, a number of physics textbooks for voltage will just use a capital V. And you're going, wait a second, it's delta V, not V, because one's potential difference and the other one's just the potential. How did they get away with that?